All right, I think we're up and running. So this is a video that I hope will help you understand implicit differentiation a little better. I'm going to take a geometric and a numerical dive into this process, and again, the hope is that you'll see the numbers work and make some connections. So explicit differentiation is when you get y alone, and then you take the derivative of the function. So we can move x squared to the other side. It's addition on the left, subtraction on the right, plus minus square root. And I'm just going to deal with the positive side of things right now. And I'm just going to take the derivative of y equals the square root of 25 minus x squared. And I think it's useful to hear this, the square root of f of x. If you're going to take a derivative of a function that looks like this, take the derivative of what's inside, f prime of x, over 2 times the square root of f of x. All right, so that's basically looking at a function raised to the 1/2 power. So you get multiplication, drop it down 1, and multiply by the derivative of what's inside. And if you clean up your act, looks like this, so that you can do it quickly and easily. Now, at the end of this video, we're going to come back and we're going to look at something we looked at in the last lesson set. X squared plus y squared equals 25, and hopefully the symbols will have a little more meaning. All right, so as I go through this, I'm trying to get a little better with maintaining the camera on the work that I'm showing. I still haven't gotten there yet, but I'm working on it. Okay, so let's start with something we know. Anytime you want to explain something to someone, always start with something you know. So if you're working with kids with fractions, for instance, and they don't know the rule of multiplication of fractions, you can start with 2 times 3 equals 6. Something you know. 2 is 4 over 2 times 3, which is 9 over 3. That has to equal 6. So what's the mechanics that make it equal 6? 4 times 9, 36. 2 times 3, 6. So it looks like the numerator times the numerator divided by the denominator times the denominator gets the job done. So we're going to look at implicit differentiation. We're going to start with something we're more familiar with. All right, so we're going to look at the product rule here. X cubed times x squared is x to the 5th. And we know that if y equals x to the 5th, y prime is 5x to the 4th. And at 2, we're going to analyze these geometric situations for x equals 2. 2 to the 4th is 16 times 5, 80. We're going up at 80 to 1 for the x to the 5th function at x equals 2. Now, if you put 2 in, you get 8 times 4 from this diagram, which is 32 units of change. If I change by just 0.01, and I make the rectangular area slightly bigger by making the side lengths, the x values 2.01, 2.01, and if I cube that, I get 8.120601. And if I square 2.01, I get 4.0401. Now, I would like to put more zeros in there to gain more accuracy, but this will suffice. And it's pretty hard to put all those decimals in and draw things here. Okay, but it looks like our new area is 32.80. Over here it was 32. It sure looks like, and again I'm doing some approximation here. I multiplied 4.04 times 8.12, so I kind of ignored those little errors that come from these drawings at the cusps. Okay, and also when I'm doing a cubic, there's a little more overlap in the layering process. But that's what we're doing. We're adding layers of area, layers of volume, and then extrapolating from there to handle other functions. Well, they must behave this way. Okay, so we've established that. Now let's go over here a little further. Move this down. I think that would be focused a little better. All right, so what's going on here? So this length, when I cube 2.01, it increased by 0.12. Okay? And over here I did one with extra decimals, right? And you can see that 0.001 divided by 0.004 is still a change of 4 units, okay, in the squaring process. All right, I digress a little bit. So where does this come from? Well, remember what x cubed was, the original side, and I am increasing by 0.01. So when I cube, it actually comes from 3x squared dx. So where did I show that? So y2 minus y1 over x2 minus x1, we're working with slopes here. So y2 minus y1, x2 minus x1 gets us the derivative of x squared, which is 2x, and I probably should have done a cubic here to show that. It's been done in other videos. Now remember what this was. This was x squared. And what I'm suggesting is that this is 0.04 is 2x dx. And that gets multiplied by x cubed here to get us that amount. Now maybe we can see the 2x dx getting my new change in y over here. This little layer of area I'm calling dy, but I'm right on the crack there. And so therefore it's hard for me to write it, so let me try here. dy. So that's my dy. Can you see it here? Your dy in this instance for x squared is 0.004. Your change in x is 0.001. And the derivative of x squared is 2x, and 2 times 2 is 4, and 4 times 0.001 is 0.004. Okay, now that's the first time I've done this with implicit differentiation, so my explanation feels a little rough. But at the same time, if we keep repeating, it should become a little better explanation over time. But remember where we started here. Y equals x squared. So instead of x squared, I could have written y. And so that change of 0.004 is really coming from 2x dx. We create the derivative when we divide the left side by dx. The derivative of x squared is 2x. But this little strip length is 2x times dx. 2 times 2 times 0.001. So if I had x cubed times y, which is the same as x cubed times x squared in these diagrams, then this is where I can implicitly differentiate. What do I get? 3x squared dx times y. Leave the second one alone. This is product rule, but I'm looking at the differentials involved in the cubing process. And I think we can see it here. 3x squared, if this is x cubed, then that length can be represented by 3x squared dx. You might have to look at the numbers again, and to see those numbers appear. But I think that's really important to see. So this is 3x squared dxy. All right, don't know what that was about. Something made a noise there. And then this one is dy times x cubed. So this is really 1 times y. And so there is our plus. Leave the first one alone. Multiply it times the differentials involved. Okay, now how do we create y prime? Well, we have to divide, both sides of an equation by dx, and I don't have the other side here. So if I divide by dx, and I divide by dx, then when I'm working with the changing function in terms of x, I get a cancellation. So if I'm looking at this and I want to shortcut it, I know I'm going to get a dx for x cubed, so all I write is 3x squared times y from a differential standpoint. Plus what? Y prime. X cubed y prime. Right? And y prime is really dy over dx. It allows me to write these things a little more clearly. And I don't have a right-hand side to the equation. If it's a constant, then it equals 0. If it's something else, you got to deal with it. But that's my attempt to move the needle a little bit in terms of what's happening with dy dx and so on and so forth. All right, so now let's go back to where we started. And let's look at implicit differentiation then. I would write 2x plus 2y, y prime equals 0. Dividing by 2 gets me x plus y, y prime equals 0. What does y prime equal? Y prime is equal to minus x over y. Now, let's go back to what we had over here. Remember what we said y was equal. Y was equal to the square root of 25 minus x squared when we did this explicit differentiation. Right? It was plus minus, but we're only looking at the positive side right now. All right, so it's that. So what's another name for y? Another name for y is the square root of 25 minus x squared. And I do believe that y prime equals minus x over y. I think the 2's cancel, and oh yes, explicit and implicit seems to merge here, and that gives us a feeling for why they're equal. Now, I did bring the box in, and it doesn't hurt to, if you've looked at the Algebra 1 videos, to trade, and you will recognize what the Algebra 1 class called the magic box. But here's a cubic, a 2 by 2 by 2 for instance, 8 units of volume. Right. Brings us back to, well, the other side of the board had 8 for an altitude on that rectangle. All right. And this is actually a derivative process. So if I make the side length of the cube, which was x, just a little bit bigger, the thickness of this cardboard makes that length just a little bit bigger, then this is the new volume that gets attached to this box. And if we look at this carefully, we can see that we have an x times x, and that is a square. X times x, which is x squared, you're looking at area, with a little bit of thickness gives this volume. And so maybe it makes a little more sense that you have 1, 2, 3 squares, 3x squared, dx, there's your 0.001. That's how the cubic is changing. Okay, so there's linkages to geometric shapes here which will allow us to extrapolate to working with integration is simply adding up all these layers of change. Let's say we go from 2 to 3, all right, then that's the net change under the curve, 3x squared from 2 to 3, which gives us the net change of x cubed from 2 to 3, which is 8 to 27, which is 19 units of change. So if I did, make sure that your dx is 0.01 conceptually. And so if we did a billion of these things, 9 zeros with a 1, 8 zeros with a 1. If we did you would get a very accurate measurement of a 2 by 2 by 2 cube becoming a 3 by 3 by 3 cube, and you would be adding up each of these layers. And you would have a calculation that adds up from 2 to 3, 3x squared dx. And if 3x squared was a rate and dx was time, rate times time would be getting you little amounts of something. And so that's why this becomes 27 minus 8, 19 units of change from the cubic function. From 2 gets you 8, 3 gets you 27, you've changed by 19 units, and you did it by looking at the area accumulating from 2 to 3. Layer after layer after layer after layer after layer after layer, okay, on the curve 3x squared. and each of these layers has a width of dx. Trying to explain a difficult concept to grasp. All right, Neil deGrasse Tyson did a video. I like listening to the man. A lot of great insights. He talked about struggling with calculus for a couple of months. What's going on? I don't get it. Notice the word I use, struggled. It's people who struggle with the math, stick with it, continue reflecting, and then all of a sudden, the lights go on. That's what we're hoping to have happen here. So, a little consideration, a little play with the geometry, a little play with the numbers. You might have to look at it more than once. It might have been a little awkward explanation in different places, but it's my attempt to put a little focus into the problems that we're looking at. All right, so I'll upload this today. Tomorrow I'll do the second half of the last lesson set that would have been done in a class. And I'm hoping you're taking it as a test and not worrying about your score, because if I give you the same thing a month from now, you'll do a lot better. Okay, have a good day.